said formal definition of derivative, you guys thought formal definition of limit, and then you just rattled it off right away. Formal definition of limit is rather large and cumbersome. This is not. Formal definition of derivative is simple, and it's simply this. The limit as h goes to 0 of f of x plus h minus f of x over h. That looks very similar to what we saw yesterday, doesn't it? What's the only difference? The x. And so what that means to us is that you have found slope at a given point, the instantaneous rate of change at any given point, right? And you've done that. Now, what we're going to say is forget about the slope at a given point. This entire function right here has a derivative. And we're going to show you what the derivative of that function is. Not too complicated. Other operators that imply derivatives, so for example, f prime, that means derivative, okay? Other operators that imply derivative, you might see d over dx. So there were two great mathematicians, Newton and Leibniz, during the time of the 1600s, and their calculus together. This was Leibniz's notation, this was Newton's notation. There's reasons to use both. I'll use this later on at some point. You might also say dy over dx. That's also an indicator that you were taking a derivative. Sometimes, and I don't see this very often, but this means a derivative with respect to x as well. But these all mean that you're taking a derivative, okay? And the derivative, again, is an operator like addition, multiplication, subtraction, division, square roots, sine, the natural log, all that stuff. So this is the most powerful operator you've ever learned. And what it does for us is it finds the instantaneous rate of change, but it can do it at not just a single point, but of the entire graph. And I'll show you what that looks like. So what I'm going to start with is I'm going to look at some interesting points in this graph right here. This graph is called f of x. And I'm going to discover what f prime of x looks like. And I'm going to pick certain x values. I'm going to start with 1, 2, 3. I'm going to start with x equals -3. And I'm going to start with x is equal to 0. And I'm going to start with x is equal to 2. Over the course of the next few days, you're going to be looking for certain patterns to develop. And there are a lot of patterns here that you can notice. This will really greatly help you as you work through your assignments and your tests. But what do you notice about the derivative at -3? 0, right?
Yeah.
What do you notice about the derivative at 0? 0. And what do you notice about the derivative at 2?
0.
Okay, so notice why I picked -3, 0, and 2 to evaluate the derivative, because it was really easy, right? And then what I'm going to do in this situation is I'm going to look at the derivative behind -3. So for example, I'm going to the derivative, say, at -5. Can somebody describe for me the derivative at -5?
Very negative.
Very negative.
Very negative. Sorry.
Somebody describe for me the derivative right around, say, -1.
Positive.
Positive.
Mid-pos.
How about the derivative at 1? And how about the derivative at, say, 4?
Very pause.
Very pos.
Oh, wow, look at that.
Everybody okay with this?
Yeah.
All right. Now, this is where it gets a little bit confusing for people. I'm going to try to make this as clear as I can. Please ask the question if this is not making sense. So I'm actually going to plot these to discover the graph of this derivative. So I'm going to start by plotting -3, 0. So the derivative of this graph has a coordinate at -3, 0. It also has a coordinate of 0, 0, and has a coordinate of 2, 0. Very good with that? Now, I'm not going to try to get all the coordinates behind -3, but rather I know that the derivative at -5 is very negative. So if I'm going to plot -5 and very negative, where would my point go? way down here, right? Somewhere way down here. And then at -1, the derivative is positive. So I'm going to go somewhere above the x-axis. In fact, you could look at the derivative at, say, -2 and estimate, oh, I feel like it's about a value of 2. And here it's at about a value of 1. So just putting a dot up here, it's not exact, but we know that it goes above the x-axis, that the derivative is positive, okay? We good there? All right. Now I'm going to look at the derivative at 1. It is negative, so therefore I should go below the x-axis. And if you look, wouldn't you describe the derivative maybe about -1? So I'm just going to plot spot at about -1. And then at 4, the derivative is very positive, so I should put my dot way up here. So it turns out that the derivative of this function looks something like that. I would say that that's an excellent, excellent sketch. Instead of putting it over here, I decided to just plot it right on top of it. I've learned over the years that that seems to make more sense. Now, the cool thing is that f prime of x, it tells us about f of x, okay? F prime of x tells us about f of x. So, I want you to glance at this section here, okay? This section right here. Notice that this section of the derivative is above the x-axis. Everybody agree? So if you look at the original function during that same time frame from here to here, what do you notice about the function f between those spots? Which direction is it headed? Up. Everybody agree? When this is headed up, this is above the x-axis. Look at this section of the derivative right here. It is below the x-axis. That corresponds with this section of f, and it is headed down. Look at this section of the derivative here. It sits below the x-axis. It corresponds with this part of f. It is headed down. See that?
Yeah.
So f prime tells us very interesting information about the original function. So every function, we could produce a derivative and glean information from that. We will be looking at graphs for quite some time. We're going to have a nice activity here that is going to really help your understanding with it over the course of the next couple days. So we say that f of x is differentiable because we can take the derivative of it. We can go ahead and sketch it. In order for a function to be differentiable at point A, we say that the following must be true. Actually, let's skip the definition. Let's just go to the 3 examples by which it is not differentiable. I think that will make more sense. A function is not differentiable, number 1, when it is discontinuous. So if I have a function that looks like this, notice how it's discontinuous at x equals 0. Therefore, it is not differentiable at that spot. In this graph, if we have a corner, I'm going to produce a graph that has a corner. This is not differentiable at -2 because it's a corner. And finally, this graph right here, somebody brought this up the other day. I can't remember which student. Might have been in the other hour, I can't remember. But here you have a vertical tangent. I'm sorry.
It's okay.
This is Kevin.
It's okay.
Yes. I do. Yes. Yes.
Guys, they copy it.
It's the queen. I think it's the queen.
The queen is coming. The queen is coming. What?
Oh my gosh, I'm shedding. Whoa.
Hey, Michaela, why don't we do this? Why don't you send me an email and give me a good time to call you, just because I'm teaching right now, okay? Yeah, just send me an email and I'll call you at some point and we can figure out what you need. I'm guessing you need a letter of recommendation. Just my email? Oh, so you just need to know my email? Yep. Yep, just kevin.gens@alschools.org. Thank you, bye. Don't do that to me, you guys.
What?
I'm not saying.
Oh,
'Cause you
don't
know
do
the-
what?
said their name. After the recording.
Oh, gosh. All right, we'll let that go. Okay, okay, so if it's discontinuous, okay, you can't take the derivative here, can't take the derivative there, and can't take the derivative at a vertical tangent. I did not talk about what differentiability means, because really it means this. The derivative from the left has to be the same as the derivative from the right. And if you notice here, the derivative from the left is going to be negative. The derivative from the right is positive, and so it cannot be resolved at that spot, okay? So therefore, the derivative does not exist there. Same thing here, at a discontinuity, you cannot take the derivative if you do not have a point. And then finally, this vertical tangent that you have here, what is the slope of a vertical line? Undefined, and therefore the derivative does not exist at that spot, okay? Let's flip it over. It says identify the intervals on which the function has a derivative that is positive and negative. Also identify the points which the function has a derivative that is 0 and the points which the function is not differentiable. I don't want to do all that. I want to keep it simple. Please work with a partner and identify where is this function not differentiable. Identify the x values where it is not differentiable. Go ahead, go.
I think so, because it's up and down.
Probably right in there, right?
Right.
Yeah.
Oh,
There is a point, but it's not. The negative point, it has no point. It's zero first, we'll figure that two.
Oh, and -2, is it? Can't see it.
I mean, there's one right there. And like, they're both going.
Everybody knows
I
that.
guess. I don't know.
Literally, I've never met a person that doesn't know that name.
Danny, let's talk about this first point. You were making a great point that they're both going down at this spot, right?
Yeah.
But it fails the first requirement, which is it continuous at the spot? No, since you have to pick up your pencil and draw the graph, it is discontinuous right here at -2. It has a corner at -1. It has a vertical tangent at 0, and then it is discontinuous at 2. How about at 1?
That's fine.
The slope is 0. It's absolutely fine. There's nothing wrong with that. Okay? See if you can identify See if you can identify the points where it is not differentiable for the next one. Go ahead.
I got a question for this. Who has actually ever met John Pepper?
Okay, I got a question for you.
Internet.
Why are you talking about He got my number.
Well, yeah, because it's up and down.
That's
I
what
guess
my
number
number. He got my number.
two, but then also like everything
He
after.
DM'd me on Instagram.
Have you guys ever seen,
Never.
have you ever seen him in person?
I have actually.
I'm really in between two information.
But did you talk to him?
Why? What? He followed us around. What's going on?
Because I think we
Oh,
also.
it's just, it's like a weird phenomenon.
Wait,
Like,
and
everyone
we
knows-
actually met him.
Everyone
We all
knows
know.
John
Is he
Pepper.
from
Austin.
Okay, I have the value of -3. Yes?
Yeah.
Because we have a corner. -2 because it's discontinuous. -1 because it's discontinuous. 2 because
What the heck's happening
The
there?
derivative from the left is not the same as the derivative from the right. In fact, the derivative from the right does not exist because you have a barcode function. And then obviously at 3 because it is discontinuous. So differentiability simply means you can take the derivative. Most all the functions that we work with are functions that you can take the derivative of at mostly any spot. Now, the exercise that you're going to be able to perform for your assignment today is this. So this is where you really want to hone in and ask questions if you have it. It says sketch the graph of the derivative of the following functions. I'd like to start with this one, this one, this one, and then come back up here, okay? Is this differentiable at every single value? No. Where is it not differentiable?
0.
0. Therefore, our graph of the derivative will be discontinuous at 0. It's going to show that as a break in differentiability at that spot. How would you describe the derivative here? Negative. And it is a constant negative value, isn't it? Give me a number.
50.
I'm going to say negative 1/2. Can everybody agree that negative 1/2 is the approximate slope?
Sure. Right.
Okay, so therefore, this has a constant value, its derivative has a constant value of negative 1/2. What is the value of the derivative on the right side?
Positive.
Positive 1/2. This takes a while to get. We'll practice this multiple days, but as you glance back at it, this says that as I look at any spot here, I say, that is a y value of negative 1/2. That means at this spot right there, it should have a slope of negative 1/2. Does it? Yeah, right here, this has a y value of positive 1/2. That means this graph right here should have a slope of 1/2 right there. Does it? Yeah, this always tells me the slope at any point. So let's look at this one right here. What would you estimate the slope of this one to be? Sure, about 1, maybe. Looks like let's just try starting here and going up 2 spots, and we would go over how much? So I went up 2 and over about 5. So I would say the slope is about 2/5. Okay, but we're just estimating. That's fine. And would you agree that you could take the derivative at every spot on here? There's no spot at which you can't take the derivative. Very good. So I'm going to put a dot at about 2/5. And I'm going to draw this horizontal line across. That means that the slope of that function is always 2/5. Never anything different. Let's look at this one right here. Is the slope always the same? No, it's not. It changes all the time, doesn't it? So this is going to look a little bit different. It's going to look a little curvy. How about this? Is there any spot which you can't take the derivative? No, you can take the derivative anywhere you want here. Which is the easiest spot to identify the derivative? At 0, the derivative is 0. And here's where you need to use some critical thinking, so follow me here. How would you describe the derivative back here at -6? It's very close to 0, right? But would you agree it's just slightly positive? So I'm going to put a dot right on the other side of the x-axis because I know that the slope is really small there, but I know that it's positive. How would you describe the slope right here?
The same but negative.
Same but negative. So it's really small, but it's on the other side of the x-axis. Yeah. I'm going to look for some other interesting spots in this graph. How would you describe the slope here? It's positive. In fact, you tell me when I get to the spot on the graph where you feel it's most positive. Right about there, okay? So I'm going to put a dot right there because I feel like it's most positive in that spot. And I don't know the exact value, I'm just estimating. Okay, about 2.5. And then you tell me when I get to the spot on the graph where it's most negative for slope. Yeah, and so I'm going to put a dot at a negative value. So this is gonna help me formulate, I know it gets to its biggest spot there. That's the graph of that derivative. Works a lot better if you try one on your own. Right now, try to sketch an approximate derivative of this graph.
Oh gosh, guys, it's hard knock life when none of my senses work. I came downstairs at like 7:20 in the morning. My dad goes, "You can't dilly-dally today, Rosa." And I said,
What?
And I said, I just wasn't planning on it. I'm not even gonna have time for breakfast. He was like, "Don't dilly-dally."
I would walk it.
Mine is just the same thing.
So this, identify this,
Oh, smart.
identify this that is the most positive.
You're trying to trip me.
It's an accident.
Good, 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 good. Good ideas.
Yeah.
Okay, all right, let's see what you got. Here's what I would have to see on your test. I would have to see a dot here. Why? Derivative is 0. Dot here, derivative is 0. Dot here, derivative is 0. Okay? Now, how would you describe the slope of the graph in between there? It's negative, so I have to be below the x-axis, right? When does it get most negative? Yeah, so I'll kind of be at the bottom. I'll be at the top, bottom. I want to graph something like that. Somebody describe those graphs for me. Give them a name. Sine or cosine waves. In fact, later on I'm going to show you that the actual derivative of sine of x is actually equal to none other than cosine of x.
Oh boy.
Yes, that is true.
I have a question.
Yes.
So how do you know how high to go? Is it always like the
You
top
don't. You
of-
don't. It is an
Okay.
estimation. So we can we can go ahead and just make an estimation, and I will give you credit either way on the test. Okay.
Okay.
All right. All right. Good. You guys are doing well. Doing well. Flip it over. We're gonna get through 2 more, and we this is for a later time. On your own, you're gonna get about 40 seconds. See if you can sketch the derivative of that. Don't talk to the person next to you. Make a guess. Go.
Wait.
20 seconds.
I'm really hoping Mr. Trans just want relax.
5, 4, 3, 2, 1. Did you have this? Sweet, good. The derivative of a constant is 0 because it doesn't have, or its slope is always 0. Excellent, way to go. All right, this next one. Can you take the derivative at every single spot there?
No.
No. So I'm gonna give you an option. You guys gotta tell me where you're at. Do you want to go through this together, or do you want to try it on your own? Okay, we'll go through it together. All right. So how would you start? What would you start with?
Zeros.
Okay, so it's derivative is 0 here. Where else? Negative 1/2. And at 0.5. Okay, great. So I've got that. Describe for me the derivative here.
Very positive.
So I should be up here, huh? Describe for me the derivative here.
Slightly positive.
Little positive, something like that. Describe for me the derivative here.
Neg.
describe for me the derivative here.
Nope, don't know.
That's super
That's
positive.
very
positive.
positive.
Super positive.
Oh.
Okay, describe for me the derivative here.
It's continuous.
Yeah, and so the
One.
the graph of the derivative is also going to have a vertical asymptote that will match. So I can draw the first part here. It looks like I've got something that looks like this. That's a really good graph of a derivative. I like that a lot. But now I've got this guy. What do you notice about the derivative? And pretend like this is a nice smooth curve. What do you notice about the derivative all the time? It's always negative. Everybody agree this derivative is always negative?
Yeah.
Therefore, its graph should always sit below the x-axis. How would you describe the derivative right here other than negative? Super negative. How would you describe the derivative of the graph here? Not as negative. So I think that that's a challenging derivative to try to graph on your own. I really do. But you guys did a really good job with that. Excellent feedback and talking there. So you're in good shape. We're gonna. This is a multi-day practice piece. You guys are gonna turn to your homework. And I used to have this where I would have people sketch them on different graphs. So if you look, I provided a bunch of graphs for you. And what I would like you to do is, if you want to put it on a separate graph, go ahead. If you want to make table values, go ahead. Or if you'd like to just draw it right on top of the other one, you just go right ahead. Whatever works best for you, okay? Do you like to draw it on top of it?
Yeah.
Okay.
Yeah.
Whatever makes best for you, whatever works best for you, okay? So there are some on the front the front should be hopefully pretty good for you. On the back side, there's something, they do get a little bit more difficult. Really try to work through them without, I don't mind if you ask for help, but make sure you try a couple times before you ask for help. How's that? Okay?
Should have a bigger one. That's your favorite flavor?
Oh no,
The
hopefully
kids sitting
Mr.
on the
Tran doesn't
counter.
watch your. Don't forget to cancel it. And cut. Never get to cancel.
Maybe cut